Welcome to qnawire.
Alright, let's go ahead and do this problem. So we're given a very particular case of F being C times R over the magnitude of R cubed, and R, forgot to write it down, is defined as the vector x comma y comma z. Okay? The surface that we're concerned about is the sphere centered at 0, 0, 0, and I am going to call the radius A simply because I normally use R, but R is already used as the vector R, so I don't want to confuse anyone, so I'm just going to use A. It actually doesn't matter much in this problem according to what the question is. It's asking us to prove that the flux is independent from the radius. So the radius shouldn't come out in the expression of the flux, and that's all we need to show. So let's go ahead and work on it. So what we want to evaluate, as usual, it's just a flux integral, so it's a double integral through S of f dot the normal vector ds. Okay. Now, I am going to focus on f dot n. F is simply equal to c over the magnitude of r cubed. Keep in mind that that is just a constant, so I can actually pull it out, and r is x, y, z. Okay, that's what our f is equal to. Now, a normal vector, as we've done in the previous problems, the normal vector of a sphere with radius a, we know that it's just going to be simply 1 over a times x comma y comma z. So when we find f dot n, we see that you will get c over a magnitude of r cubed times x squared plus y squared plus z squared. And as you know, this is simply equal to r dot r. And then we know that r dot r is the same as the magnitude of r squared. In fact, furthermore, we know that x comma y comma z is the parameterization of this the sphere, and the normal vector is 1 over a of x comma y comma z. So we know that all of these expressions can be represented in terms of a. So that'll be a cubed. This will be a squared. Okay, so all of this simplifies to c over a squared. Okay, now this is still a constant, so I can just pull it out from the flux integral. And then all I need to do is to evaluate this expression, which is equivalent to the surface area of the sphere with radius r. And then we know that that is equal to 4 pi a squared, because the radius is a. And as you can see, the a's cancel each other, so the flux is 4 pi c. Long story short, this last expression does not depend on the value of a at all, so we really don't need to care much about the radius, hence proving the fact that the flux is independent from the radius. And that is the end of the proof.